Okay, today I will show you my homework 9.22U. It's about Laplace transfer function. Okay, so the topic of this research is experimental report, block diagram rendition, and Laplace transform. So the main I think is transfer function simplification. Okay, so the table of the content is experimental objectives, significance of the experiment, detail, solution, process, and conclusion, supplementary notes. Okay, and the experimental objectives, master block diagram rendition. Proficiency in applying series, perennial and feedback loop rendition rules, as well as Marson's scan formula to solve transfer functions for complex control system and understand physical meaning. Clear the physical implication of each block, summing junction and the feedback paths, establishing the relationship between block diagrams and the system dynamic equations, and grasping multi-loop uh, simplification logic, learn to handle complex structure like nested feedback, feed-forward composition, and memo system, developing a systematic analysis approach from inside out. Okay, so the establish undefined modeling thinking, combining block diagram reduction with RLC circuit modeling to understand the control logic across electrical and control system, laying a foundation of mechatronic and automation analysis. And the significance of the experiment, you can see the theoretical foundation. Block diagrams are core to control system analysis. Laplace transforms are and reduction are fundamental for understanding stability, dynamic response, and frequency characteristic. Engineering application widely used in motor control, robotics, and power system. Reduction enable quick derivation of transfer function for controller design and performance optimization. And miserical applies to all LTI system and transfer directly to mechanical, hydraulic, and pneumatic molding, making it a universal cross-domain analysis method. And academic research, found foundational for modeling complex system and survives as an entry point for advanced theories like multi-variable and robust control, supporting further research. And you can see the step 1 is problem define. We input x, Laplace transform of the input single, and output response, and the goal drive g. G is equal to the y-is multiply x-is. So the system structure contain two feedback loops, one feedback forward pass and three zero forward blocks, responding a typical NIST multi-loop control system. And the method selection, you can see the block diagram reduction and the Marson's gain formula. And the method 1, the inner loop reduction, you can see the result is replace the inner loop with a single equivalent block with scan G inner. Then the outer loop and the feed forward. The new structure is consists of equivalent inner block G3 in series and negative feedback pass with gain H2 G1. Reduction rules for negative feedback closed loop gain equal to G forward multiply 1 plus G forward H feedback. Then we get a conclusion, then we get the result. So we can get the final loop reduction. Use this method. The method 2 is Mason's gain formula. You can see the function about TS. Where the permanent ribbons, you can see these three answers. Then we identified forward pass. Forward pass analyze from input X to output Y. There is only one forward pass present in this system, and the pass gain conclusion. The gain of the single forward pass P1 is the product of the serial black. And identify loops, you can see the 3 loop feedback. And then the final conclusion and the physical meaning. The final transfer function is just like this. Okay, that's all. Thank you for your listening.